endowed professor in information theory and applications. I say that because he has information theory in his chair endowment. He has done his bachelor's work at Israel at Ben Gurion University, and then he did a PhD in Stanford, and he worked at Bell Labs in Mathematical Sciences Research Center, and then he worked for a financial company for 2 years, and just to again stress, he then returned to academia, not to make more money, and he has been with UCSD since 1997. His webpage states, while Professor Orlitsky is a theorist, his research deals with concrete communication scenarios. Orlitsky is actively studying interactive communication. He also studies communication complexity. His work in speech processing and recognition is of both practical and theoretical interest. He's looking at information theoretic approaches to speech processing, touching on issues including recognition, compression, and synthesis. His work in learning theory primarily about online learning and he maintains an interest in investment theory based on the work he does as quantitative analyst for a Wall Street investment firm. He teaches information theory and algebraic coding, and we are very fortunate to have Alon as our next lecturer. So let's see.
Thank you very much. You can hear me? Okay. No? So maybe just move them up a little bit. Better? Okay. Thanks. Okay. So thank you very much, Eileen, for the kind introduction. Finally, I realized what real applications iPads have. So, and speaking of Eileen, I want to thank all the organizers of this school, and especially Gerhard and Eileen, who I think created something out of nothing, and it's an idea that, you know, now that it's done, I think people realize how useful it is. And I also want to thank Eileen for actually moving me from where I used to live, which looked practically like that, to something that, relatively speaking, looks like that. So for all of these things, thank you. Okay, so so we're going to talk about probability estimation over large alphabets, and this is mostly joint work with many of my past and current students. Started with Prasad Santanam, Krishna Viswanathan, and Junan Zhang, and then some of my later students, Jayadev Acharya, Yokendu Das, Anandu Lipula, Nikola Jevtich, Shengjun Chan, and Pan, and Sajama worked on it as well. And all of the works will be mentioned here. Okay. So going to discuss, and basically this is a 1-hour talk, and I'll just talk, you know, twice as slowly. So hopefully I'll be slightly coherent. Okay, and we'll try to cover 4 topics: distribution modeling, classification, probability estimation, and data compression, talking about all of them from a unified viewpoint, which we call patterns. And because these are very basic problems, then a lot of famous people have worked on them, and we'll mention them as we go along. And so there'll be even some flora and fauna that get involved and so on. All right, okay. So yeah, and I have to make one last apology here that this is actually not a very good talk, because if you take a good talk, then you take things that are different and you make them look the same, and things that are complex and you show that they are simple, and things that take some applied problem and build a theory around it, and take things that are boring and actually show they're interesting. And in this talk, we're going to look at things that look different and try to convince that are clearly the same, try to convince ourselves they're different, things that are simple, and we'll make them look complex, take a theoretical problem and try to argue that it has few applications, and by the time we're done, something which is interesting to begin with will be very boring. So, okay. Sorry. Okay. So we all grew up learning that a rose by any other name would smell the same, and science, being equally beautiful, should produce the same results no matter which language it's conducted at. So, for example, let's say we try to find a distribution of swine flu cases in different countries. So, for example, we want to say that 30% of the cases are in the US, 20% are in Spain, and so on. So, what we could do is we could look at some incidents that occur, and we see that there is one in Mexico, one in the US, Mexico, Spain, and Mexico again. And based on these occurrences, we want to find the distribution between the different countries. So the results we should get should be the same that if a French researcher is conducting this experiment and observes that the first case is in Mexique, and then États-Unis, Mexique, Spain, and Mexique. Okay, so we hope that the distribution that we get should be the same as the distribution that the French researcher gets. And what do we mean by the same? We mean that the probability that we'll give, the American will give the USA, is the same as the probability that the French research will give États-Unis. Okay? And the result should be the same not only if we conduct the research in a mortal language, but also if we do it in the immortal language of math and call the first country we see 1, and then the second country that we see number 2, and then we keep those numbers. So now when we see Mexico again, we'll have 1 again, and Spain will be a third country, and then Mexico again will be country number 1. Okay? So this representation is what we call the pattern. Okay? And basically what we do is the first country that we see, we call it 1, and then the second 2, and we keep those numbers. So what we hope now is that the probability that the mathematician will give 2 is the same as the probability of the USA. Okay? And it seems like this should trivially be so. Okay. So just to make sure we understand, let's do another example. So suppose we want to see the probability of a horse winning a race. Then we can look at some horses that won. We see Barbaro won, and then Seabiscuit and Barbaro and Barbaro. Then if we look at the pattern, what would the pattern be? Barbaro is 1 is the first horse, then 2, and then 1 and 1. Okay, so that's the pattern of the sequence. And again, we hope that the probability of Barbaro, we think, should be clearly the same as the probability of 1. Okay? So these are what we claim are the same, and we'll try to convince ourselves that maybe they're different. Okay? And if they're different, then hopefully they're better. Okay? Right. Okay. So let's see what patterns do. What they do is they replace each symbol by its order of appearance. So for example, if the sequence is ABBA, what is the pattern? 1, 2, 2, 1. If the sequence is bananas, it's 1, 2, 3, 2, 3, 2, 4. And if we want to play Jeopardy, 1, 2, 1 is the pattern of which word? Yeah, like mom, dad, I, or it doesn't have to be letters, could be red, blue, red, and it can even be people, Gerhard, Alon, and Gerhard. So, okay, and last one, which word will have the pattern 1, 2, 4? None will have that because after 1 and 2, we must see 3. Okay, all right. So, what patterns do is they capture the structure and the frequencies of the symbols that we see. Okay, but they ignore the symbols themselves. So we don't care if the first one is M or D and so on. We just care that the first one is the same as the third, and the second was different. Okay, all right. So what are the 4 problems? So we've seen how 2 of our characters belong here, and let's talk about the first 2 problems: distribution modeling and probability estimation. So what are they? So in probability estimation, we want to associate probabilities with outcomes. So for example, we want to say that Spain has 20% of the cases, so the probability that the next case will come from Spain is 20%, Mexico has 50%, and US has 30%, and Seabiscuit has 25% of winning, and Barbaro 75% of winning. When we do distribution modeling, that's the second problem, then we want to disassociate the probabilities from the outcomes. So we want to estimate just the probability multiset. So instead of saying that Spain has probability 20% and Mexico has 50% and so on, we just want to say the set of probabilities are 50%, 30%, and 20% without saying which country has what probability. We just care about the multiset of probabilities. Okay? Or we want to say that one horse has probability 3/4 of winning and the other has probability 1/4 without saying which horse has what probability. Okay? So these are the two problems. And we'll actually start with the second one with distribution modeling, the one where you just want to estimate the probability multiset. Okay? So this is what we want to estimate, just the probability multiset. And what is the first question to ask about this problem? Either priors, but even maybe before that is who cares? Right? If I'm going to bet on a horse, then I want to know which horse is going to win. If I'm going to buy a stock, I want to know which stock is likely to go up. Why should I just care about the set of probabilities without knowing which one is associated with which outcome? Okay? So let's look at some potential applications. So first one is if a lot of people are interested in the number of different species that exist in a given habitat, or the number of gene mutations that a certain gene can have. All these just count the number of elements in the support set. They just want to say, okay, in this case, there'll be like 5 species. One of them is 50% of them, and so on. Okay, so we just want the cardinality of the set. So that's clearly just a function of the set. Okay? I gave this talk, and there was someone sitting. He was working for a company that produces drugs. And the way they produce drugs is they take a bunch of molecules that they know are related to what they're trying to do. These are legal drugs. And they, because she's worked on a similar problem. So, and they mix them together and they see if this molecule that they get works. And if it does, that's good. If not, then they continue, they try again, they mix them again, and so on. And they want to know when they've covered 90% of the stable molecules that they can get. And then it's not worth because they'll start getting a lot of repetitions. So again, this is a function of just the probabilities of getting each molecule and not which molecule has appeared. Okay. Or if you're going to build like a wireless network that you want to make sure will work 95% of the time, then you don't care about the probability that Eileen will talk or the probability that Gerhard will talk. We just care about the probability that how many people talk with what probability. There are so many people that talk with probability 0.9 at any given day and so on. So we just care about the set of probabilities, not who is associated with which probability. And there are many, many other applications. Clearly in information theory, we care about entropy as just this is sufficient. In general, whenever you care about statistics, that's what you care about. Just, okay. So the answer to who cares is everyone, or at least we do. And so, to see one simple approach, let's imagine that we get there's a UFO landing, and the first message that we hear consists of 60 ats and 40 pounds. Okay? And we're going to analyze this sequence, and we're going to assume independence. So first order, we're just going to assume that each symbol is generated independently of the other. And if we do that, we'll determine how many symbols are in Martianese. How many different symbols? 2. And what are the probabilities? 0.6 and 0.4, right? So again, we don't care about which symbol has a 60% probability and which one is 40%. So we'll just say that the two probabilities are 0.6 and 0.4. Okay. And which methodology did we use? Well, we could say we used either empirical frequency, we saw 60% ats and 40% pounds, or maximum likelihood, which will the same, and we'll describe maximum likelihood in the next slide. Okay, so what is maximum likelihood? We're looking for the distribution that maximizes the probability of what we have observed. Okay? So in this case, we observed the sequence consisting of 60 ats and 40 pounds. So we call the probability of at p and the probability of pound 1 minus p. So the probability of the sequence is going to be p to the 60 times 1 minus p to the 40. Okay? And that's by the independence that we're assuming. And so we can just differentiate and equate to 0, and we get that it's maximized by p, which is 0.6. Okay? So therefore, the probability of at is 0.6, and the probability of point is 0.4, And so the set of probabilities is 0.6 and 0.4. Okay. So this maximum likelihood agrees with empirical frequency always, not just in the case of two symbols. So for example, if we saw 20 ats, 50 pounds, 30 ampersand, then the probabilities will be, the maximum likelihood will give you 0.2, 0.5, and 0.3, which will sort, because we don't care about the order, so we'll just always sort them and write 0.5, 0.3, 0.2. Okay? And as we can see, this works well. So these are very reasonable answers. And that's because maximum likelihood, or empirical frequency, works well for small alphabets. Like here we have alphabet of size 2 or alphabet of size 3, and we saw 100 samples. But as we'll see in the next slide, they work poorly when the alphabet size is large compared to the number of samples that we have. Okay. All right. So to see that, instead of more Chinese, let's look at a different language, more Chinese. And let's assume we go to China and we observe, oh, finally we got a joke. Right. And we see this, okay? So I'm told this is what it means, okay? So clearly what we'll see, or not clearly, it's likely that what we'll see is 100 symbols, all of which are distinct, right, if we go to China. And if we did maximum likelihood on the sequence, then what would the alphabet size be? 100. And each symbol will have probability because each one appears once, probability of 1%. But this is clearly a poor model, right? I mean, after we see all of that, we're not going to say that Chinese has 100 symbols. Okay, what will we more likely say? How many characters do they have? A lot of them. So we'll say that maybe a large, possibly infinite alphabet, right? Because that would explain why everything is different. Okay. So let's do a thought experiment and say that because we don't care, we're considering the problem where we don't care about the association between the elements of probability, like I can't even pronounce this symbol, right? So we just care about this multi-set of probabilities, then we can just replace them by the pattern, right? So consider the pattern instead, okay? So instead of doing maximum likelihood on the sequence, we're going to do maximum likelihood on the pattern. Okay? And that's where we thought it should be obviously the same, because we're just replacing a symbol by this one by 1, this one by 2, and so on. So it should give us the same answer. Okay? So let's see. So what is the pattern of this sequence? Or all of them are different? 1 up to 100. And that just signifies, this pattern just signifies that we took 100 samples and all of them were different. Okay? And which distribution will maximize the probability of this pattern? Uniform over how many symbols? Okay, so if you had uniform distribution of 100 symbols and you took 100 samples, then you expect to see some repetition. And here we did not see repetition. So what will maximize will give you a higher probability? It's exactly the distribution that we would say, right? Large. It's exactly if you had a distribution over a large, possibly infinitely number of elements, then you will not see any repetition. Then you'll see this pattern 1, 2, 3, and so on. Right? Okay. So it's clear that they're not the same. Patterns are not the same as sequences. Not the same as sequences. They're different. And what we want to see now, and furthermore, it's clear that they work better for when the alphabet is large, like in this case when you have infinite alphabet, let's say. Okay, so what we want to see is why that's so, and also what happens when you have a smaller alphabet. Okay, all right. Okay, so let's see the difference between sequences and patterns. So we're assuming that the sequence is generated independently and identically. Okay, so it's IID. Okay, so in at least most of this talk will assume IID sequences. Okay, and then it will induce a probability on the pattern. Okay, so let's see. So if we call the pattern Psi, so then for example 1 to 1, then what is the probability of observing a pattern? It's the probability of all outcomes with that given pattern. Okay. So for example, if the alphabet consists of A, B, and C, and for simplicity, let's say the probability of A is they're all equally likely, probability 1/3. And if we take one sample, what is the pattern we'll get? 1. And what is the probability of 1 is clearly going to be 1, right? We'll always get it. If we take 2 samples, then we can get 2 patterns, either 1/1 or 1/2. What is the probability of 1/1? In this case, it's the probability that what we observed is either AA, BB, or CC, right? Those are exactly the cases will give us the pattern 1/1. Okay, and what is the probability that we'll see that? It's 3 times 1/9, right? So it's 1/3. And that's reasonable because 1/1 just says that the second was the same as the first. That's exactly what this means. And because they're equally likely, then this will happen with probability 1/3. Okay? And what is the probability of 1, 2? It's the probability that we'll see the A, B, A, C, all of these sequences. And that happens probability 6 times 1/9, which is 2/3. And that just says that if, in this case, the probability that the second will differ from the first is 2/3. Okay? So we see that the patterns are not distributed IID, right? Because the probability of 1 is 1, probability of 1, 1 is not 1, okay? And therefore, we get different math and different results, okay? So what we want to do there, then, is do maximum likelihood not on the sequence, but instead on the pattern, okay? So given a pattern, for example, 1, 2, 1, 3, we want to find the highest probability p hat that this pattern can get and the distribution that achieves it, and that's. So, for example, if the length is 1, what is the highest probability that the pattern 1 can get? 1. And it will be achieved by which distributions? Any distribution. Right? What is the highest probability that 1, 1 can get? I took 2 samples and I got a pattern 1, 1. What is the highest probability this could happen? 1. And it will happen if the distribution is what? Is a constant distribution. Right? Always gives me the same outcome. How about 1, 2? What is the highest probability that that could have? Also 1? Okay, so 1/2 is, again, if we limit ourselves to coins, to distribution over 2 symbols. But if we don't insist, we just say we took two samples and we saw 1, 2. Infinite, that's in Chinese, right? Okay. Okay, so for length 3, 1, 1, 1 will have, again, probability 1, and 1, 2, 3 will have probability 1, again. So the first interesting one is 1, 1, 2. Okay? And so because we're looking at IID sequences, the probability of 1, 1, 2 is the same as probability of 1, 2, 1, same as probability of 1, 2, 2. Okay? So if we solve this one, we'll solve everything of length 3. Okay? So what happens here, for example, is let's just for concreteness, let's say we flip 3 coins and we get heads and tails. Then what would sequence maximum likelihood be? What if we do maximum likelihood on the sequence on heads and tails? It will tell us that the probabilities are what? 2/3 and 1/3. And we want to see now what happens for maximum likelihood. Okay? So we flip coins, 3 coins. We get heads and tails. We want to see what will maximum likelihood tell us. Will it tell us there are more coins and so on? All right, more sides. Okay. So what we'll show is that the highest probability that 1, 1, 2 can get is actually a quarter. Okay? And we show it the usual way. We show that you can get a quarter and that it's at most a quarter. So to show that it's at least a quarter, let's just take a fair coin and flip it 3 times. So what is the probability we'll get 1, 1, 2? It's the probability we'll get either heads, heads, tails, or tails, tails, heads. And that's the sum of these probabilities, so it's 1/4. Okay? So if we just take a coin, we'll get 1, 1, 2 with probability 1/4. Right? Okay. Now we need to show the more interesting part, and that is that any other distributions, either on just 2 values or maybe on more values, will not give us more than a quarter. And that's what we want to show. Okay? So what is the probability of 1, 1, 2? So it's the summation of all possible outcomes, x, that x appears twice, that some outcome x appears twice, and then something other than x appears. So it's p square x times 1 minus p of x. Okay? So we want to maximize this over all distributions, not just over 2 elements, but over any number of elements. So we can write it as summation of p of x times 1 minus p of x. But when we group them like that, it's clear that this product is at most a quarter. Okay, so it's at most summation p of x times a quarter. And now we get that's at most 1/4. So this shows us that any distribution over 2 values, 3 values, any number of values is going to give us a probability which is at most a quarter. Okay? And then there's only one inequality, so it's easy to see when you get equality here. You get equality exactly when these values, this product is 1/4, meaning one of them is half and the rest is also a half, right? And it has to be half for every value, so just 2 values and it's a half. Okay, right. Okay. So it's achieved by p of x, which is half for all x. So that tells us that if we get 1, 1, 2, then pattern maximum likelihood will tell us that the probabilities are equal, actually. Okay? So if we get heads and tails, then sequence maximum likelihood tells us 2/3, 1/3, whereas pattern maximum likelihood tells us 1/2, 1/2. And the question is, which one is more logical? So remember that the infinite alphabet for Chinese pattern made more sense. If we can convince ourselves that this is like the smallest possible alphabet of size 2, pattern also make more sense, then there'll be hope that also in between they make more sense. Okay, right. Okay. So let's see here. Okay, so so which of those makes more sense? So okay, so remember that we are not trying in this problem. We're not trying to find the probability of heads and the probability of tails, just the probability multiset. Okay, and we'll show that in that case. We'll show two cases, so we show that half-half actually is more logical. Okay? So, so first of all, we're flipping 3 coins. So we cannot get in each of them, each side appearing 1.5 times, right? So cannot get that. So 2 and 1 is the closest to uniform that you can get. Okay? So that's one possible reason. Okay? And another possible reason is, let's look at the possible outcomes. What are the possible outcomes? Either one side appear 3 times, if we flip a coin 3 times, either the same side, heads at heads, or one side will appear twice, and one side will appear once. Okay? Now, what we have seen is this, one side appearing twice and one side appearing once. We saw heads, tails. Okay? So what we did not see is one side appearing 3 times. Okay? Now, if you take any distribution other than half-half, for example, 2/3, 1/3, that will increase the probability that one side will appear 3 times. Like here, this side will appear 3 times, and that's what we have not seen. And therefore, it will decrease the probability of what we have seen. If one side appeared twice and one side appeared once. Okay? So therefore, again, half-half, which will better explain what we saw, which is that one side appeared once and one side appeared twice. Okay? So we see 2 reasons why actually half-half is more logical. But I agree with you that, that maybe we're not yet convinced. So we'll see some examples. So we saw that, that when the alphabet is infinite, PML is more pattern maximum likelihood more logical. When the alphabet is binary, we try to argue it's more logical. And the question is what happens in between. And we'll see that in 10 minutes. Okay? But before that, I want to do another example, which is maybe a little more complicated than what we've seen before. So, so the highest probability of 1 is 1. The highest probability of 1, 1, and 1, 2 is also 1. The highest probability for length 3 is what we've just mentioned. And if this is too easy, if it looks too easy, then let's try the next one, which is 1, 1, 1, 2. Okay, so after this, 1, 1, just add a single 1. Okay. So to do that, let's talk about math Olympiads. Okay, so so this is an annual competition, as of course many people here know. I'm sure many people have participated. It's an annual competition for high school students, and began in 1959, and it's the oldest science Olympiad. So since then, there are many different types of Olympiads. There's a chemistry Olympiad, physics Olympiad, soon to be pattern Olympiad. But and it takes place over 2 days. Each day is 4.5 hours and 3 problems. Each problem is 7 points, so the maximum is 42 points. And they award medals with the ratio of 1 to 3 to gold, silver, and bronze. And they do it in such a way that about half the participants get a medal. Right. So, clearly very bright people participate in it, and correspondingly they go on to receive other awards later on. So this is a very telling chart about people who received medals in the math Olympiads and then went on to receive the Fields Medal and other medals. Okay? So, so as you can see, pretty much, once you get the gold medal, you just go to sleep for about 20 years, and you wake up with the Fields Medal. And I actually am lucky to know about 5 of the people here, so I know a little bit, at least Lovash and Babai and Hastad and Peter Shore and Alexander Razborov. And you'd think I'm saying it to brag about all the people I know, but actually when you look at this more carefully, then knowing me is not a very good sign. Okay? Unless you're concerned with the Navalina, Knuth, or a Gödel Prize, and then it's a very good thing to know me. So, right. Okay. So, okay. So because they give the prize, the medals to half the people, I guess it's not a huge deal to win a medal, so to speak. Okay. So the bigger challenge is to get a perfect score. to get all 42 points. And because many of these people are very smart, clearly, then essentially every year there'll be a few people that will get the full score. So here 22 people got the full score, 5 people, and so on. And you can see for the longest time everyone got the full score until they went to Eastern Europe, and and the Eastern Europeans know how to construct interesting exams. So then the highest score was 39, and it was achieved by 3 people. Okay. So so let's look at the second problem from the IMO of 1999. It's the following. It says, let n be a fixed integer, and we want to find the least constant, c, such that this inequality will always hold, okay, for any real numbers, okay? And okay. So a standard solution here, almost everyone that looks at it would observe that, and this I took from the web, that the inequality is symmetric. You can exchange xi and xj, and also homogeneous. All the terms here have degree 4, so the powers are all 4 here. And so we can assume, for one thing, that the xi's are decreasing, just permute them, and we can assume that they sum to 1. Okay, so let's see what we mean by that. And in that case, we can simplify the question to just say, so we assume that each of them, it's decreasing, and then they sum to 1, and we just want to maximize this sum. And just to see why. So this is the original equation, okay? And then what we can do is we can divide by summation of xk to the 4. So we moved it here to here, 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 and here, x to the 4. And then we'll call each of those terms a new xi. So what we get is that we want to look at the smallest constant c, such that summation of xi xj times xi squared plus xj squared is less than or equal to c. Okay? And so what is the smallest constant? It's just the maximum of this value. So that's what we want to see. Okay? So what does it have to do with patterns? Or before that. So this is the first step. Okay? And then comes the solution, where you assume that you have some sequence, and then you combine 2 things together. And so first of all, one problem is that you assume that you have a sequence x1 up to xk, so this will only apply for sequences with a finite number of values, positive values, okay? And then you combine 2 values like that, and then you do something that is not super intuitive, and then you go to show that if you do that, you'll increase the value, and then you continue, okay? So let's look at the pattern interpretation. So we want to maximize this value, summation of xi, xj, and so on, such that each of them is positive and they sum to 1. So let's just call them what they are, probabilities. So we want to maximize this sum. And we can write just multiplying. So we can want to maximize summation of pi cube pj plus pi pj cube, okay, over all I less than j. And this is just combining the summation of all I not equal to j of pi cube pj. Okay? But this is the probability of a pattern. Right? Which pattern? 1, 1, 1, 2. Right? This is exactly the probability of the pattern 1, 1, 1, 2. Right? Because then we look at all possible pi's and pj, and we look at the probability that I appeared 3 times, and then another symbol j appeared. Okay? So the PML, so the question that they had was just finding the maximum probability of 1, 1, 1, 2, namely the pattern maximum likelihood. 1, 1, 1, 2. Okay. So what we'll show is that this probability, the highest value is 1/8, and it's achieved by half-half, again a coin. Okay. And again, we'll show that it's at least that, and at most that, and at least will be again by a fair coin. So if we flip a fair coin 4 times, then the probability of 1, 1, 1, 2 is either 3 heads and a tails, or 3 tails and a head, and 1 single head, so that's 1/8. Okay? And what we want to show, so that's why it's at least 1/8, and we want to show less than or equal. That's what we'll show next. Okay? All right. Okay. So how do you show it at most 1/8? So we'll just go over a few things. So if you want to find a simple upper bound on the product of 2 numbers, what is the most natural thing to do? The arithmetic geometric mean inequality. So we're looking at the area of A times B. The area is maximized under the circumference constraint if it's a square, so a plus b over 2, so we get that. Okay, and you get equality if a equals to b. Okay. Second thing we can observe is the probability of 1, 1, 1, 2, which is what we want to do, is the same as the probability of 1, 1, 2, 1, right? Because it's IID, so it doesn't matter if we saw heads, tails, or tails. Okay. A third thing is, what is the sum of the probability of 1, 1, 1 plus the probability of 1, 1, 2? Can you express this as the probability of another pattern? It's the probability of 1, 1, right? Why? Because 1, 1, 1 means that x1, the first thing you observe x1 is the same as the second one. x1 and x2 are the same, and x3 is also the same as x1 and x2. And 1, 1, 2 means that x1 and x2 are the same, and x3 is different. When you sum them up, you just get that x1 is equal to x2, and that's probability of 1, 1. Okay? So that's another thing we need to remember. And the last one is, what is the probability of 1, 1 times the probability of 1, 2? So that's the probability that x1 is equal to x2 times the probability that x3 is not equal to x4. Remember, it's IID, so we can talk about x3, x4. Okay? So it's a probability that x1 is the same as x2 and x3 is different from x4. So that's the probability, because again, because they're independent, it's a probability that x1 is equal to x2 and x3 is not equal to x4. So let's call this event E. So note that because x1 equals x2, then amongst x3 and x4, at most one of them will be the same as x1. Cannot be that both of them are the same as x1. So there are three cases. Either this event occurs and x3 equals to x1, or this event occurs and x4 equals to x1, or this event occurs and neither of them equals to x1. Okay, so these are the three cases. Okay. Now, what is this is, can we write this? What is the pattern of this, that x1 equals to x2 and x3 equals to x1 is x2, x3 is x1, and x3 is not equal to x4? What is the pattern? 1, 1, 1, 2. What is this pattern? 1, 1, 2, 1. And what is this pattern? So x1 is the same as x2, x3 is not equal to them in x4. 1, 1, 2, 3. Agree? Okay. So that's the other thing, last thing we need to remember. Okay. Right. Okay. So with that, so this is what we need to know. 1, 1, 1, 2 is the same as 1, 1, 2, 1. This is what we've just said now. A times b is less than or equal to a plus b over 2. And 1, 1, 1 plus 1, 1, 2 is 1, 1. Okay. So, so the probability of 1, 1, 2, which is what we want to calculate, is therefore 1/2 times the sum. And that's at most, we're going to add another pattern, 1, 1, 2, 3. So it will increase this probability. And then by this inequality, it's the probability of 1, 1 times the probability of 1, 2. And then using the arithmetic geometric mean inequality, it's at most the probability of 1, 1 plus the probability of 1, 2 over 2 squared. Okay. But what is the probability of 1, 1 plus the probability of 1, 2? It's the probability of 1. It's the same idea as this. It's actually simpler. Okay. So it's probability of 1 squared. And what is the probability of 1? 1. So it gives you 1/8. Okay. So we get that the highest probability is at most 1/8. And it also, this proof also applies to infinite distributions, not just finite ones. And it's intuitive. You can follow here each step and see where it comes from. Okay, and also shows you where you get equality. Again, you have equality. You need to get equality here and equality here. Equality here you get if there are only two symbols, so this probability is 0. And equality here you get if the two of them are the same, have the same probability, so it's 2 elements and 1/2. Okay, so this is Math Olympiad problem number 2. Okay, so okay. So hopefully we understand what's involved in calculating the maximum likelihood probability of patterns and so on. So let's talk about some theoretical results you can get. So we'll only do a summary. So first, some modeling properties. So first you can show that pattern maximum likelihood is always achieved. You can find distribution that achieves it. And then you can show that it's smooth in the sense of majorization, sequence maximum likelihood. So for example, if the sequence maximum likelihood looks like that, then pattern maximum likelihood will look more uniform, okay? Which in some sense is what you want, because if you don't have enough data, you want to say things are more uniform than they should be. Okay? And the other one is that it converges to the distribution, and it's uniform convergence. So we don't need to worry about this, but in terms of L infinity, it will converge to the right distribution. And uniform means that it's independent of the alphabet size. The alphabet size does not enter into this equation, just the number of symbols number of samples that you took. Okay. However, what we can prove here is quite weak. So we would like to improve. We need to improve this bound n to the 1/4 is actually very slow convergence. So then, for some simple patterns, we can calculate the PML. So if the pattern is binary, for example, 1, 1, 1, 2, 2, so only two symbols were seen, then you can show that the distribution in the PML is binary. So there are only two values, P and Q. Once you get to just P and Q, you can just solve an equation and find it. Okay. And we typically we'll call this like mu1. The number of ones we've seen is mu1. The number of twos we've seen is mu2. And so for binary distribution, if you take the symbol that appeared the most times, so mu max is here in this case it will be 4, and mu min will be 2. If the difference between them square is at most n, then the PML is half-half. And this is, in some sense, it's good, because if you have a binary distribution, then the standard deviation is going to be square root of npq, and if it's half-half, then it's going to be square root of n over 2. So you expect to see one of them appearing n over 2 plus square root of n over 2, the other one appearing n over 2 minus square root of n over 2. So in terms of standard deviation, if you look at the number of times heads appeared minus number of times that tails appeared, it should be roughly square root of n. Okay? So what this tells you is if the difference is less than square root of n, it will tell you it's uniform. If the difference is bigger than square root of n, it will tell you it's not uniform. So it makes sense. Okay? We can also solve all ternary patterns like 1, 1, 2, 3. And for those patterns, a similar thing happens. If for every two values, like 1 and 2, you get the same type of inequality, then again it's uniform. So now you want 1 and 2 to appear roughly the same number of times, and 2 and 3 appear roughly the same number of times, and so on, then it will tell you it's uniform. If the pattern is skewed, so one element appeared many times and everything else appeared once, it tells you that there is one value with probability, which is R over M, and then you have something like a continuous distribution that gives you all these other values. Okay? If the least number of times that an element appeared is at least log of the number of symbols you've seen, then the support will not increase. It's not like Chinese that you've seen 100 symbols, but you said the support is infinite. So if the minimum number of times that an element appeared is at least logarithmic in the number of samples, then there will be no support increase. And conversely, if the largest number of times is that an element appears at most log of square root of m, then the support will increase. And there's some other results. Okay. So these are theoretical results we get, but I think we can maybe learn a little bit more from the experiments. So here's the uniform distribution. Let's over 500 symbols, uniform distribution of 500 symbols. And we took 350 samples. Okay, so in this particular run, there are 2 elements that appear 6 times, 3 elements appears 4 times, 13 appeared 3 times, and so on. 161 elements appeared once. So there's a total of 242 elements that appeared, and 258, more than half, that did not appear. Okay, so if you did the pattern maximum likelihood, the sequence maximum likelihood, empirical frequency, then you'll get this. These are the 2 elements that appeared 6 times, then the 3 elements appeared 4 times, and so on. Here are the 161 elements appeared once, and these elements did not appear at all. So if you do sequence maximum likelihood, you will not realize that you'll miss like more than half of the elements, and you'll miss the fact that the distribution is uniform. You'll think it looks like this, like a staircase. Okay. On the other hand, you can do pattern maximum likelihood, and you can just ask, which is equivalent to just asking which distribution over any number of elements, and could be uniform or not, which distribution maximize the probability that if you take 350 samples, you'll observe this pattern. Okay? And when you do that, you get this distribution. Okay? So it somehow figures out that there are roughly 500 elements, and it's roughly uniform. And here, it also thinks that there's an element with a higher probability, probably because here there are some elements that appear 6 times in this run, and elements appearing 4 times, but nothing appeared 5 times. So something maybe a little unlikely happened. Okay? So there's nothing that appeared 5 times, so it gets there. Okay? So you can say, okay, maybe we were lucky in this particular instance. So we ran 12 times. These are all, yes?
Trust your algorithm, because it seems to be like to find this PML is very computationally very difficult.
Correct.
Like it's polynomial optimization, it's an
right.
ugly thing. So So how should I trust this green curve that comes out of your?
Yeah, so I think this is the purpose of exactly. You're totally right. So the algorithm is complicated. I'll say a few words about that in shortly. So exactly the purpose of these slides is to build a little bit of confidence, show you that it works well in many cases, and then hopefully it will work well in other cases. But the only other thing I can say.
My question is not exactly this, which is how do I believe that this green curve is exactly the PML?
Oh, okay. So we don't know, and hopefully, if you get the exact PML, it will look better, but we don't know. It could be that this approaches the PML, but it's not a PML, and the PML is much worse. That's possible, but yeah, we don't know.
Building on that point, is it, when I don't know the alphabet, is it even clear how to optimize? Like, is it even clear, obviously decidable? Or?
It is decidable in the sense that you can try over all sequences, and you can go. That's right. So you can. So we have a conjecture which we work on here, which is that the largest, this is one of the open problems. So what is the largest alphabet increase that you could get when you observe a sequence? So it makes sense that, okay, so if we see Chinese, 1, 2, 3, 4, 5, then the alphabet size is infinite, right? But let's ignore the case of the infinite part. When would you say is the next case that that is the closest to this maximum increase? Would be probably, you would say, instead of seeing 1, 2, 3, 4, 5, I see 1, 1, 2, 3, 4, 5. So there's only one element that appeared twice, okay? And then everything else appeared once, okay? So in that case, you can solve that case, and then the alphabet size that you get goes from infinity, goes to m choose 2, roughly, or m squared over 2.
Any repetition will be a certificate that the alphabet is finite.
Okay.
Or not really?
No, well, okay. So there's an issue that I didn't want to get into. So the way this works is this. If, let's say that you saw Chinese, right? Then the alphabet size is, you take uniform distribution over k elements. If you increase k, the probability that you'll get 1, 2 even, okay, will increase. But we'll never get 1. We'll just approach 1. The way we get around this is we said we have a collection of discrete probabilities, P1, P2 up to Pk. Could be a P1 up to P infinity, and then a continuous part. In which case, 1, 2 will come from just a continuous, just taking continuous part. Okay, if you do that, you say have a sequence of discrete probabilities, P1, P2, P3, could be infinite, and a continuous part. Then you can show that the discrete part will always be finite. You can show that. And you can also get a bound on the number of distinct probabilities there. You can get that. Okay. And then we have a conjecture, so that actually, essentially all the problems here are open. So one question is whether it's really true that if you take 1, 1, 2, 3, 4, that this pattern will maximize the increase of over the alphabet size, which is very logical. It will be shocking if it's not, but we don't know how to prove that. So these are 12 experiments, and we arranged them here more or less from the best one to the worst one visually. And as you can see, in almost all of them, PML works very well, and definitely in all of them works better than SML. Okay. Right. So this is
Variation in the green curve can just be not that PML does not work, but that somehow your algorithm did not get the PML.
That's right. So there are two issues. One is whether PML is the right thing to do, and the second one is whether algorithm achieves the PML, and we don't know either one. Right. Now, if you take the same distribution over 500 symbols, but now instead of 350 samples, take 750 samples, then now sequence maximum likelihood will do better. We'll get more of the elements, but still missing like 120. And if you do pattern maximum likelihood, we'll get you almost the exact thing, and this repeats now in all experiments. And these are all the experiments we did. Okay. All right. So here is an experiment with a staircase instead of uniform distribution, because we don't restrict the distribution of the PML to be uniform. It's whatever it comes out to be. So this is a staircase, 30,000 samples. Again, if you do that, it's over 15,000 elements. If you do sequence maximum likelihood, you'll miss about a third. If you do pattern maximum likelihood, you'll get that. Here is a ZIF distribution, which is a distribution that people like to use to represent natural phenomena. So it decays like some constant over I. And here again, 15,000 elements. We took 30,000 samples. Here we need to take 30,000 samples because the probabilities here become very small. This is logarithmic scale, so these probabilities are very tiny. And so if you do, if you take 30,000 samples, you'll observe about 9,000 out of the 15,000. So this is the sequence maximum likelihood. This is the pattern maximum likelihood. So these are synthetic distributions. If you can try them on real distributions. So these are distributions of last names according to the 1990 census. So every 10 years, the census is being taken, and there's a big debate as to whether they should go from house to house and send everyone an envelope, or whether they should check it statistically. This year, for example, they hired 1.2 million people to do the census. And while some people think, oh, it's a waste of money, other people think it's a job stimulus. So here is from 1990, the frequencies of last names. Smith was the most likely, 1%. Johnson, the second, 1.8%. And these are the cumulative. You just add them up, okay? And these numbers go down. You can get this data from the internet. And it goes up to about 19,000 names. Below that, they all give you 0. So we just took the numbers up to here, for which we know these values, okay? And so these correspond to 19,000 names, which are about 77% of the population, or about 280 million people, okay? So from this distribution, what we did, so 18,000 last names based on about 230 million, so this is the distribution. And what we did was we just sampled from this distribution 35,000 times, and we observed 10,000 names. So this is the sequence maximum likelihood, and again, this is the pattern maximum likelihood. Okay. So, so some notes about this is that sequence maximum likelihood, I'm comparing things here to sequence maximum likelihood. That's basically for pedagogical reasons, just to illustrate the difference between sequence maximum likelihood and pattern maximum likelihood. The other techniques that people use, but they typically make some assumption about the underlying distribution and a prior and so on. So sequence maximum is a simple one that does not make any assumption, and it's comparable to what we're doing in the sense that one is maximize the probability of the sequence, and the other the probability of the pattern. Okay. So here the only assumption, unlike these techniques here, we're just assuming IID, and we're assuming IID because it's sampling. So and you can replace it by other distribution non-IID if you want. And another comment about patterns. So patterns, the concept of a pattern was used before. So people looked at restricted growth functions, which represent the number of patterns, and prediction by partial matching, Arberg, Starkov, and Smith in '97. And then in statistics, people looked at exchangeable random partitions and allelic partitions and pinbox processes, which are all equivalent to looking at patterns, but they've not, what we don't think they've used is pattern maximum likelihood, which is what we use here, and attenuation, which we'll get to in the second part of the talk. Okay. So should I continue for 10 minutes or yeah? Okay. Okay, I won't. Right. Okay. So so just because we have 4 topics, and you better finish one before. Right. Okay. So we talked about applications of patterns, and the first one was for population estimation, and this goes back to the early 40s, where people were trying to estimate the number of butterflies in what was then Malaya and now Malaysia. And there was a very famous work by Fisher, Corbett, and Williams, which we'll come back to a little later. And what Fisher was, of course, is credited with coming up or popularizing maximum likelihood. So he clearly realized what we have seen, that maximum likelihood on the sequence does not work. So they assumed some Poisson distribution with the gamma prior, and with that they estimated the number of butterflies. And then there was some more work on the number of new species by Good and Toulmin, and people look at mutations and strain and so on. So there's sensors, Lang Tong from Cornell and so on. So there are many, many works on estimating the population based on samples. So Rudiger told me about some work at EPFL where they want to estimate how many people are in a crowd by the number of cell phone uses that they observe. Okay, so in one popular application is for the determining Shakespeare vocabulary. So Shakespeare wrote about 900,000 100,000 words, of which 28,000 roughly are distinct. Okay, and half of those distinct words appeared only once. So his vocabulary was so large he could just reuse a word, forget about it, use another word, forget about it. So, okay, so in 1976, Efron and Thisted wrote a paper on estimating the number of species and subtitled "How many words did Shakespeare know?" And they said that if Shakespeare wrote another 900,000 words, then there'll be another 11,000 new words in addition to the 28,000 that he has used before. Okay. This work was, I shouldn't say forgotten, but was not that well known until about 10 years later. A poem was found at a library in Oxford. It's called "Shall I Die?" And it goes like this. Shall I die, shall I fly, lovers, baits, and deceits, and so on. People thought it was possibly written by Shakespeare. Of course, we know it was written by an information theorist, because the next stanza is, shall I tend, shall I send, shall I sue and not rue my proceedings? So he's clearly thinking about his next publication. And in this poem consists of 429 words, of which 9 are new. These are some of them. Perhaps the most interesting one is bizots, which means to make dull or stupid by either infatuation or drunkenness. So by the time we're done, you can say you're bizotted. And then Efron and Thisted applied the technique again, and to this poem, they wrote a new paper, and they showed that you expect to see about 7 new words, and 7, statistically speaking, is close to 9. So it's considered as evidence that Shakespeare could have written this poem. Now, if you do the pattern maximum likelihood, if you get this distribution, then you can do the same thing, right? And you can do it not just for the number of new words, because now you have the distribution. You can say, okay, if I took another sample, how many things do I expect to see that I have not seen? And if you do it, you get 6.98. So the point is not that it's like infinitesimally closer, but that it gives you roughly the same thing without any assumptions here. You just do maximum likelihood, and you just apply this simple calculation. Okay. So, and one other thing to note is that they have considered number of words in an equal size, or at least a chunk of the paper is about that. And we'll come back to this maybe after the break. Okay, so just trying to see why they're considered equal. What happened if we wrote an equal size? Because clearly we would also be interested how many words if you wrote like 10 times as much, and so on. Okay, so we can maybe stop here and continue. Is that?